Hey guys, and welcome to probably the much anticipated 102 CDE, 102 CEM revision video. So I've had a reasonable response to the hot questions, which is very good. So I don't know how long this video will take. It'll just be as long as it takes me to get through all of the questions. So here are the actual questions. So there are quite a few of them, which is good. It means that you've got lots of things to ask. So, first question isn't exactly related to the exam, but I'll answer it anyway. It says, what are the equations we're going to use to calculate power efficiency in the machines lab assignment? So, I'm going to assume that this is very similar to previous years, and that the power calculation is going to be done in roughly the same way. So, what I'm going to do is I'm going to show you the mark scheme from the last year's assignment. So this is a sample from the Machines Lab marking scheme from semester 1 from 2016 to 17. So this is the one that the same you guys would have done if you were in the second year now. So this one's to calculate the input electrical power, the output mechanical power, and the efficiency when the armature current is at a certain voltage. So I'm assuming this will be done in a very similar way. So as I said here, as each of the groups are different, we're going to look at the data and apply the correct equations. So the way we did it last year was we had the input power P in, which is equal to V IL, so the voltage you're applying and the current through the load. You've got the net mechanical power, which is EBIA minus P power per rotation. So the efficiency of the load under the motor is EBIA minus P rotation divided by VIL, which gives you this whole term here on the top. Basically, all this equates to P net mechanical energy divided by P in. Okay, so that's the efficiency of the motor. So those are the equations. You can replay this video, you can have a look at it and see how that works, and then your P rotation that we had here is equal to the power in the core plus the frictional power, which is V minus IARA times IAO, which is equal to EBO times IAO. So remember, EBO was the generated power back EMF, and IO is the current through the armature. So that was the way it was done last year. So you had 1 mark for doing the correct calculation at each stage in the machines lab. So I'll probably just go through the other things. So the other one we had last year was to produce the output mechanical power and input mechanical power. So we had P mechanical power equal to T omega. There's a negligible load present of that, and input electrical power is VILO, which is equal to P in, which probably helps with this. And your P in, you've got your copper field losses, you've got your armature losses, core losses, and your mechanical losses, which then produces your P mechanical energy. And that was just some descriptive questions for the first bit. So hopefully these equations will help you. So again, P mech is equal to T omega, so your torque times your omega. T omega wants to be 0, so both T and omega are non-zero values. And the input electrical power is equal to V ILO, which is equal to P in. There's all your power losses. And then your net input power P in is VIL. Your net mechanical output power P net mech is equal to EBIA minus P rotation. And your efficiency is equal to this equation here, which I already went through. And your P rotation is P core plus P friction, which is equal to this here, which is V minus IARA times IAO, which is equal to EBO times IAO. So that's basically going through and giving you some feedback on the marking scheme from the last year, and hopefully you can then use that knowledge to apply it to the mark scheme for this year. Okay, let's go on to the next question. So the next question on the list is, what is flux leakage? So flux leakage is one of the losses in a magnetic circuit, and that would have been covered in video number 14, topic number 14. So let's have a look at those specific slides. So flux leakage is when not all the flux produced by the primary coil intersects with the secondary coil. Okay, so if you're obviously got your current flowing through your coil, and you've got the number of coils to produce a magnetomotive force. So what happens is, if in an ideal case, all of the flux generated here in the primary winding is going to link with the secondary winding, and hence you're going to get an ideal transformer style situation. However, in reality, as you can see here, you've got phi 1 here, which is flux that leaks away from the main flux and loops back in on itself and doesn't intersect with the secondary core windings. So what happens there is you're using energy to create a magnetic field which isn't intersecting with the second coil, and hence it isn't transferring its energy into the coil, which means it's wasted. So that's why flux leakage is a loss, because you're using energy to create a magnetic field and flux that is hence doing nothing. So that's why this is the leakage flux. And the way you can get around that, as I've said here, is to tightly couple the magnetic core. While I'm on this, I might as well go through the other losses. You've got your copper losses, which are due just to the fact that these wires here are going to be made out of copper, and obviously putting current through them is going to make them heat up, so you've got I squared R. You've got the iron losses, so you've got the hysteresis losses from continuously moving around the hysteresis curve, the BH curve, and in doing so energy is taken and that will heat up the core. And you've got eddy current losses, so if I just move my picture across here, then as you can see here on the right hand side of the screen, you've got a small current that's induced because of a change in the flux with respect to the change in the time, and that will try to oppose the change in the coil current. So one way to get around hysteresis losses is you can use things like a nickel iron alloy. So you can use nickel iron alloys, and that reduces this exponent term in your hysteresis equations. So that means that you're losing less energy as heat in the core. And to prevent eddy current losses, what you do is, instead of having one big mass of material which the eddy currents can flow around, what you do is you slice that into lots of thin pieces, you laminate them with a varnish, then you glue them all back together again. So as you can see in this situation here at the bottom, you've got less area that the current can induce in, which means the induced current is going to be smaller, which means the opposition is going to be smaller. And because all these separate layers are insulated from each other, the current can't go from one layer to the next. But that doesn't affect the magnetic principle. And as you can see here in this figure here on the left, then you can actually see the slices here in the material. Okay, and I give another shout out to Wikipedia for letting me use these images in the first place. And again, if I move on, that can then allow us to build this, which is our ideal transformer model, which is what we can actually use to find out what the losses are. So you've got 4 components, which represents those 4 main losses. So I hope that has been helpful to you. Okay, let's have a look at the next question. So the next question is kind of an easy one, so it's can I explain the exam structure. So I'm going to go full screen on this. So the exam, as you know, we're using a new exam template this year, which is a faculty template. So that template is going to be different visibly from the template that you've seen on the past papers. Okay, so it will work in exactly the same way, except that it will look different to start with. The second main difference is that, unlike the previous exam papers where you were asked to answer 4 questions from a 6, is that there is now a compulsory section A which everybody has to do, and an optional section B where you pick 2 from 4 questions. So you still do 4 questions out of 6 like previously, except this time you've just got a mandatory section. So that mandatory section A is comprised of the old question 1, which is here's a circuit, find the total resistance, find the current supplied by the source, use current division or voltage division to find the current through a voltage across a particular component. Then you might use that to find a power maybe. Then a fault happens, so either you get an open circuit, short circuit, the current's connected from one point to another, etc., etc. Something might happen, so you need to understand that, and I believe there was a hot question later on asking more about that, so I'm going to leave that until then. And then you have to find the change or the new current or the new power in a particular component. So as long as you know those methods, you'll be fine. There's nothing to worry about. The other mandatory question is the old question 4 from the 4 from 6 exam paper, which is the AC circuit question. So here's an AC circuit. You've got multiple resistors, multiple capacitors, multiple inductors. So your first step would be to get just an RLC circuit which has one resistor, one capacitor, and one inductor. You can then find the complex resistance, complex impedance, and complex inductance. Obviously, resistance is real, so that's your real component. Your complex capacitance is minus J over 2 pi FC. Your complex inductance is J 2 pi FL. And then you can add those together to find the magnitude and phase of the total impedance. You can then use that using Ohm's law, except now instead of it being I is V over R, it's I is V over Z. And remember the rules. So when you're dividing magnitudes, when you're dividing vectors, you divide the magnitudes and subtract the phases. And if you're multiplying vectors together, you multiply the magnitudes and add the phases. Okay, and then again, you might be asked to either add vectors together on a phasor diagram. So you might be able to add the three together. So you find the coordinates of the three, add the three coordinates together for the real and the imaginary parts, find the new magnitude and phase, and then plot it. Remember to bring a ruler and a protractor because it is also useful, so you can use those as a check mechanism. And again, or you might be asked to draw one again, so the protractor and the ruler will come in handy. So that's your mandatory section A. Your section B is, and again, so section A will come from, so question 1 will be from about topics 1 and 2. Question 2, the old question 4, will be coming from topics 9, 10, and 11. Question 3, 4, 5, 6, which is in section B, so you'd answer 2 out of the 4. So questions 3 and 4 would be all about the advanced circuit analysis techniques, so mesh analysis, nodal analysis, superposition theorem, equivalent circuits, capacitor charging, discharging circuits, things like that. So it's going to be a mixture of those three. So basically everything from topics 3, 4, 5, 6, and 7. Okay, so they're going to be the topics used for questions 3 and 4, and they're going to be the more mathematically focused questions. Okay, so they're going to be heavy on maths, light on description. Okay, so excuse me, I've been recording a lot of videos today. So that's going to be questions 3 and 4. Okay, they will be in Christina's old format. So if you look at the past papers, you can see the format and the style Christina used. Obviously, going forward from the January 2017-18 exams, I'll be taking over writing those questions again, and that's mainly. So the questions 3 and 4 is where it differs between 102 CD and 102 CEM. So I'll come more about the differences for that when I do when we have a 102 CEM cohort. Questions 5 and 6 will be based more about the machines, magnetics, and power generation. In the first attempt basis, because you're doing the machines lab practical experiment, you won't have a question based on the machines lab in the first attempt. That will probably pop up on the reset because you're already doing those learning outcomes in the lab, so it's pointless to repeat it. So we're over assessing the same things. So your question 5 will be mostly based around magnetics, which is topics 13 and 14, which is all about magnetic circuits. About there'll be a slight calculative question to start that off, similar to the questions 3, 4, 5, 6 from magnetics tutorial. I think it's tutorial number 9. And again, the rest of it will be descriptive, so it could be about talking about magnetization, it could be talking about hysteresis curves, or those losses that I mentioned earlier on in this video. So it could be anything around that. It won't include actuators though. So don't worry about anything about actuators because actuators are classed as machines. Okay, and the question 6, which will come from topic 16, which will be all about power generation. So the fossil fuel powered, the nuclear power, the renewable energy, all that kind of thing. Okay, and again, the questions 5 and 6 would also be the same for 102 CEM students. So the only questions that would be different for 102 CEM than from 102 CDE would be questions 3 and questions 4. So whereas the electricals will do the advanced circuit analysis techniques, the 102 CM students will do operational amplifiers, transistors, MOSFETs, diodes, and some superposition theorem, and potentially also some capacitor charging discharging theory as well. But for the electrical 102 CEM students, the transistors, the operational amplifiers, the MOSFETs, the diodes, all that will be in your 101 CDE, so that's outside the scope of that module for you, which is why that's the slight difference between 102 CDE and 102 CEM. So I hope that has been useful, giving you an idea of the new format of the upcoming exam. So let's get back to the hot questions. So the next one was, for the machine site report, what's the difference between plot a speed torque curve for this machine and on the same graph insert a typical speed torque curve? So essentially what you want to do is you want to plot two graphs on the same Excel spreadsheet. Okay. What I'll do is I'll just make a very basic video on Excel on how to plot the two different diagrams together, but essentially you'll have the speed and the torque data, and you'll have to plot that for the machine that you did. Okay, and then on the same graph you'll have to insert a typical speed torque curve for a series machine, so you can see the differences between different machine types, because I believe, if I remember correctly, you guys did a shunt excited machine for your machines lab. I'll just double check that just to be on the safe side. So if I just go back to here. So I believe you did a shunt series. So if I go to practical assessment and go to the motor assessment brief, and then open that like so. If Word wants to work, that is. Come on, Word. Yes, I don't care if you open it protected view or not.
2,000 years.
So as you can see here, it said that you're using a shunt excited motor exercise, and if you go through that, you didn't obviously do any other motor configurations, so that was the shunt. So the purpose of that question is actually to show you the difference between a speed torque characteristic for a series excited motor and a shunt excited motor. So here I've just got a basic Excel spreadsheet, so I'm going to show you how to plot both of these. So as you can see here, sorry, I keep scratching my nose because I've got a bit of a cold coming on, so apologies about that. So what I want to do is I want to select all that data, I want to go to insert, and I want to insert a chart. So it's going to show me what type of chart I want, so I'm going to go for that. And as you can see there, because I plotted that, so I've got my input on my x-axis, my output on my y-axis, and as you can see there, it plots it in the two graphs in different colors, so you can see what they are. Again, it showed you what they are. It's taken the data from the legend, so you can actually use that. You can add a chart title. What I can also do is as well, you can add a chart title there. You can add chart axes, titles. You can put errors in there. You can actually put the divisor in there if you want to. So again, I could double click on that and click. So for the I want to say that's the output, and I want to say that's the input, and I'm just going to write example chart up there. So that gives you an example of how to write how to put on a basic graph, and then you can copy that, paste it into your own work, so that you can then do your analysis and submit it on through Turnitin. And the link for Turnitin is now available for you to use. So I hope that has been useful, showing you how to plot for two different graphs. The next one is, can I explain exercise 3, topic 3? Now I've looked through the lecture notes and I can't actually find, there's no exercise 3 in topic 3. So you can see if I quickly go through these lecture slides, then you'll see there's an example 1, a matrix form, an example of a current source, an exercise 1 and exercise 2. So there isn't actually a exercise 3, so there's not much more I can do with that one, unfortunately. So apologies about that. If you want to email me, whoever that was, I'll try and clarify the situation for you. So the next one is topic 3, exercise 2. Confused with the resolution. Why in exercise 1 we have 2 currents, I1 and I2, and we solve them in R3. On exercise 2 we have 3. I think I can explain that for you. So let's have a look at the solutions for this. So this is actually the solution sheet for this particular exercise. So you'll see I deliberately in this part, this first part here, I used an I3 to show you that if you try using an I3 instead of an I1 plus an I2 or an I1 minus an I2, you wouldn't be able to do the superposition, the simultaneous equations, because you'll have 3 unknowns and you won't be able to do that. So that's why I said to solve it, we need to use I3 as I1 minus I2. So person is exactly right who wrote that question. I was just emphasizing that point in the solution. So when I put the I1 minus I2 in, I can then have my 2 simultaneous equations, which I can then solve to give me my answer. So yes, that is perfectly correct what that person said. But I just put that to emphasize the fact. So the next question was, can you specifically go through each topic for each question of the exam? I think I already did that. I understand there's more than descriptive, but which ones are for which topics? Yeah, so I think I already did that. Not directly related, but why isn't there a video for topic 8? I did say topic 8 was formative, so that was all about semiconductor physics, and the only way it would have helped you is if you looked at topic 16, particularly with the solar panels, because you need to know that for the p-n junction material. But apart from that, yeah, I haven't had a chance to record that yet. It will pop up. I will post a video. I don't know if I'll get it done before the start of semester 2, but it is on my list of videos to record, but I thought this one was more important. So yeah, plus I've ordered some equipment so I can do some props for that video as well. Okay, the next one is, can you go through nuclear power generation again? Do we need to know the difference between a boiling water reactor and a pressurized water reactor? Okay, so someone's obviously been watching topic 16's video. So yes, there are 2 main power generation techniques for nuclear. So just let me pull up those slides. So this is a particular slide. So as you can see, it's got the red boundary around it, so it's an important piece. So basically, you'll just need to know about a conventional power. You won't need to know the difference between a pressurized water reactor and a boiling water reactor in this case, just the boiling water reactor one, which is this one here. So again, the idea is that you've got the control rods, which are lowered in or out of the reactor to control the reaction. That reaction generates heat. You've got a coolant mixture which goes through this purple pipe here, purpley pink pipe here. That's the radioactive material, so that can't leave the containment vessel, which is used to contain any radioactive material. It goes into your heat exchanger here, which then heats the water into steam, goes through the steam line, which can then go through the turbine. That turbine then moves the generator, which generates the electricity. Then you've got your cooling tower using condenser cooling water to convert the steam back into water, which is then pumped back into the containment vessel, which then gives you the steam to generate again. So key terms for this would obviously be the containment structure, the control rods, which are made of an absorbing material, and things like that. If I'm just going to bring up tutorial number 10 as well, because there's a useful question in there for you to look at. So as you can see here, question 7 actually states about what is the design of a nuclear reactor. So if I look at the solutions for that, then you can see that that's a very similar diagram to the one that was on the PowerPoint presentation. So you've got the control rods, you've got the moderator, so there's a control reserve, the moderator's in there, you've got a coolant, which is used to feed into the heat exchanger, so no radioactive material leaves the containment vessel. That's used to heat the steam, which goes to the generator, and the condensed water comes back from the cooling tower. So again, neutrons are created by fission, and they need to be slowed down, so that's the purpose of a moderator, which is typically carbon, graphite or graphene, and heavy water, which is deuterium dioxide. Ideally, fission is produced at a rate of 1 fission for 1 neutron. So you've got lots of neutrons produced, so you need control rods to absorb those extra neutrons, and they're typically boron-coated steel. And as we said, by lowering them in or out of the reactor, you're increasing or decreasing the number of neutrons, and therefore you're controlling the rate of the reaction. The heat produced is used to make steam, as we said. However, steam can't be used to cool the reactor, otherwise it becomes radioactive. So like I said, you use a coolant which flows through the heat exchanger, which then exchanges the heat from the coolant into the water and hence into the steam. It's all contained in a reactor vessel made of concrete, and that's to prevent the reactor from being damaged from external influence. There was actually a train video where they did actually drive a train into a nuclear reactor flask to see if it would damage it as well. So I think I'm actually include that in this video if I can find it. So yeah, and again note that if these words underlined are the key words, so they're actually showing how it relates to the key parts of the reactor, which is shown here. The other typical thing is this question here, which compare the advantages of a hydro plant with a fossil fuel plant in terms of capital, running costs, environmental aspects. So that's important, particularly environmental aspects, because it relates more to UK spec. So I'm going to go through that question. It wasn't specifically asked, but I'm thinking it's a useful question to know. So for example, here we go, fossil fuel and hydro plant. So in terms of costs, fossil fuel plants have a low capital cost per kilowatt hour to install, whereas a hydro plant, you need a big work to build a dam or whatever, so the capital cost is very high to set up. So fossil fuel plants are low cost to set up, hydros are higher. Running cost of a hydro plant is low because it's water, so there's no running costs for it. Whereas the fossil fuel plant, you need to buy fuel in, so there's a running cost for that. The only maintenance cost for the hydro is maintaining the dam, because you don't want the dam to break and flood a huge area. And the environmental aspects are burning coal can produce greenhouse gas, which can cause climate change or global warming, whereas in hydro, there's no gas emissions occurring, but it does have an effect on wildlife, so things like deforestation, shifting in wildlife, and those fish trap videos that I sent before. So yeah, so hopefully that will clear up a few of those misconceptions. I'm not going to play that clip because I found it, of the train running into the nuclear flash, just to show you how tough they make these things, so they can actually withstand huge impacts. I probably should have put this in the main lecture video, but since I'm going to make this into a playlist for future years, it will be included on here as well. So enjoy the video.
And £7.75 to stage the crash. One of the containers was put on the railway track and the train driven into it. James Wilkinson was there to see it happen.
Demonstrators who broke through the safety fence delayed the test for 5 minutes. But the train, a Type 46 diesel locomotive, was soon on its way from its siding 8 miles away, accelerating to a speed of nearly 100 miles an hour. The 50-ton flask had been carefully laid across the track. 2,000 specially invited guests watched from a safe distance. As the train approached, the 4-year research program reached its climax. Now for a closer view of the crash. The slow motion camera shows the train's death throes even more clearly. The computer had predicted that the train and the flask would be carried up to 200 yards beyond the impact point. In the event, they didn't get quite that far.
The flask ended up here, battered but virtually undamaged. The train itself was a total write-off.
Careful checks on the pressure inside the flask showed that there hadn't been the slightest leak. The CEGB were delighted.
These flasks are ultra safe, and people shouldn't worry at all about the transport of spent fuel. The general public really ought to be satisfied. I mean, it's been expensive, but I think they ought to be satisfied, and that makes it worthwhile.
But some opponents are cynical.
It's the best flask they have. It's obviously been very carefully checked beforehand, and so there is no question of any human error problems and so on, which I personally believe would be more likely to cause a breach if anything was.
The CEGB are, however, convinced they've proved their point. They say if this doesn't reassure their critics, then nothing will.
Yeah, so thank you to Fleetline119 YouTuber for posting that video and letting me use it in this video. Okay, so next one is, this may sound dumb, but what's the difference between an open and a short circuit? Okay, as I said in week 1, there is no such thing as a stupid question. So just let me boot up Multisim and then I can show you. Okay, so what I've done here is I've just drawn a very basic circuit. I've not bothered to change any values because I'm not going to do the calculations or anything on this. So I'm just going to show you the principle. So for example, say this was your question 1 on your exam. You've actually gone through, you've actually calculated everything, and now it's the bit where something happens to the circuit. So for example, I'm going to say something's going to happen to R3. Okay, so if R3 becomes an open circuit, I'm effectively increasing the resistance of R3 to a very big value, which essentially means I'm just getting rid of it like that, because the resistance is going to be so big, it just acts like an air gap, so nothing's going to go through it. So essentially, you've removed that component from the circuit. Okay, so that's an open circuit. Okay, so the current would still flow around here. It would still flow from R2, R4, and the only difference is this combination here, instead of it being a parallel combination of R2, R3, and R4, it would now just be a parallel combination of R2 and R4 instead. So which would produce a slight change in the total resistance, which you could then use to calculate. So if I put that back, and now I want to say it's a short circuit. So if I'm doing a short circuit, I'm effectively bypassing that by putting a wire loop by it. So effectively I'm lowering the resistance by putting in a short circuit. So by doing a short circuit, I end up with a situation that looks like that. As current follows the least resistive route, the current's going to flow from R1 and it's going to see the short circuit and go straight through into R5. So effectively, it's going to eliminate R2 and R4 from a circuit, so then that parallel combination ceases to exist and we will get a situation that looks like this. So remember, with an open circuit, you replace it with a gap, and with a short circuit, you replace the component with a wire. Okay? Again, one of the other issues that might happen is, for example, say, just going to put that back in there. So, for example, I'm going to put that in there like that. And, for example, say I want to connect, so say this point here down to ground. So if I connect that down to ground like that, then the current flowing through R5 is going to see this node here, or this is going to be a load. This is going to be the easiest path because it's a short circuit, and as a result, the circuit would just become that because it would bypass R6 and R7. So when you're dealing with open short circuits or connecting a short to another point in a circuit, then again, you need to just look at the circuit, see what happens, and always draw the new circuit on an exam because that will really help you. Okay? So I hope that's been useful. So remember, short circuit, you replace it with a wire. Open circuit, replace it with a gap. And if you're shorting something out, look at how it will affect the circuit. Okay, so going back to our questions, we've got the next one is, what is the difference between a simple cycle and combined cycle coal-fired fossil fuel plant? Confusing as, well, I'm not going to say that. So yeah, okay, so let's have a look at that. So again, this comes from topic number 16 on the exam. So I'm just going to bring up those lecture slides now. So again, here's your basic process for a fossil fuel plant. So you've got your coal, which comes in here, goes into a pulverizer, so it's mashed into pieces, so it's very fine, and so it can burn a lot easier. You're probably asking why would it burn? Well, actually, if you blew flour, like normal baking flour, because it's very fine, into a flame, that would actually go woof and expand. So that's why we use that, because it's very fine, has a larger surface area, burns more easily. And here's just another quick YouTube video of someone actually throwing flour into a fire to show you the effect of it. So
2, 3. Oh my god!
Yeah, you don't want to do that. So yeah, it causes massive explosive reactions. So please don't try that at home. Yeah, so again, thanks to YouTube and the YouTube channel Dan Starts a Fire for letting me use that video. So it's gone into the pulverizer, and then goes into the furnace where it's burnt. You can see here's the heat exchanger here. Then it flows through into the turbine here, which then turns the generator, which then makes electricity. So that's a standard coal-fired plant, which is about 30 to 40% efficient. It's poor efficiency because of a turbine and a condenser. Okay, so a simple cycle station, which runs at about 566 degrees C, typical conditions for a 500 megawatt station. You've got about the high pressure system, which is 2,300 psi or pounds per square inch. The low pressure system, which is at 565 pounds per square inch, and again, an efficiency of about 38 to 40%. So here's a figure. So you've got the coal and gas that comes in, it's heated in the boiler. So you've got your primary coil here, which produces a high pressure steam, which turns a high pressure turbine. That steam is then returned to the boiler to be reheated, goes through again now into a low pressure steam turbine, and both of these turn the alternator, which generates the electricity. So again, this is a very useful very useful diagram and process to know. The combined cycle was developed after the simple cycle, when there was more push for oil and gas rather than using coal. So this was in the 80s and 90s. So with this, you can actually achieve efficiency of over 50%. And by doing that is you've got the gas coming into your gas turbine. That gas is being burnt. It's producing the steam. Again, you can have high pressure, low pressure steam systems, but that's basically not the focus at this point. So that's why it's not included on this diagram. And they're using to turn the alternator. However, when you're burning things, if you've got a lighter, then you're going to have a hot vapor coming up. So even though it's not in the fire itself, you're going to get the hot air rising. You can actually use these exhaust gases to heat the water, which will make steam, and then you can feed that into the steam turbine, and then that is why you get over 50% efficiency. You're not only using the heat from the actual fire to heat the water, you're using the hot exhaust to heat water as well. So you're getting more energy out of that material that you've burned, which is why the efficiency, as I said earlier, is a lot higher. So, I hope that's explained that. So, next question, please. Okay, so it's the penultimate question. So, how do you find the voltage across a capacitor after a defined period of time? And how do you find the instantaneous voltage? This person has an issue with exact time periods. Okay, so let's look at the first one first for capacitor, to find the voltage on the capacitor at a particular point in time. So that would be from topic number 7. Okay, so if we look at topic 7's notes, so that leads us to this slide here, charging a capacitor from a voltage source. So you've got your voltage source here, you've got a resistor here, and you've got a capacitor here. So by knowing the capacitor and the resistor value, you know what the RC time constant of the charging curve will be. So knowing that RC time constant gets us to 63% of our final saturation value, and getting 4 time constants gives us practically 98%, 97% of the saturation value. So you'd use the curve VC of t is equal to Vs plus A E minus T over RC. So the A is to set the boundary conditions. So essentially what you would do is you would plug your time into this value here, so into the T, and that would give you the voltage at that specific point. So if we just spin on again so that we can look at it for a standard charging curve like this, then if we wanted to find the voltage at a specific time, say 2 seconds, so we could put this for 2 seconds in here, so it'd be minus 2 over RC times V, do the exponent of that, and there's 1 minus that times Vs. So it would be Vs of 1 minus E to the minus 2 over RC, and that would give you the time. And you can just change by using this time parameter here. It does work the same for different boundary conditions, so you just substitute the T in here. So that's how you do that. Okay, I believe the second half of this question was about the instantaneous voltage in AC circuits. So that material comes from lecture 9. So let's just jump ahead to the lecture 9 material. So that essentially comes from this slide here. So if you've got the Vt is equal to Vp sine omega t plus phi, then what you can do is, you know what omega is, so it's 2 pi f. So you know what omega is, you just substitute the time that you want in here, which is t, and then you would know what the peak is, so you can sub that in and you can use that. So, and you will find what this value is here. Also, if you look at this slide of lecture number 9, which is slide number 12, then you can see here you've got Vt equals x. So you substitute it in, you want to find the time at 2.3 seconds. So you substitute that in and you can punch that through and you can get your answer out. So basically gives you the instantaneous point at any point in that waveform. So it's just using the standard AC waveform equation. There are some examples of that in the material which I'll let you have a look at yourself so you can reinforce that material. Remember, learn by doing, people. Learn by doing. So that brings us to our last hot question for this revision video. So let's have a look at that now. And this question says, can you go through the types of magnetic material again, please, and how the BH curve are related by that curve thingy? Okay. Okay, so this material comes from topics 13 and 14. So I'll start off with the different magnetic material types. So that comes from topic number 13. So that's from this slide here. So we've got ferromagnetic materials. So they're really good magnetic conductors. So they have a permeability value something from about 100 to 10,000. And they're things like iron and steel, so they're really good ones. Here you've got paramagnetic materials. So they're just slightly higher than unity. So they're kind of like electrical semiconductors, for lack of a better phrase. And they're things like aluminum and platinum. And then you've got diamagnetic materials, which have a permeability of less than 1. So they're like magnetic insulators. And they're things like copper and silver. So if you did get asked this on an exam, that would probably be worth about 6 marks. So 1 mark for each of the permeability values and 1 mark for each of the examples of the materials. So I think the next bit was about the BH curve and the magnetization. So I'm going to go through that now. That's more relating in topic number 14. It is touched on in topic 13, but I'm going to jump to the main bit in topic number 14. When you're plotting this curve thingy, as someone quoted it, it's actually a magnetization curve. So you'd have the magnetic field strength, H, on the bottom, and the magnetic flux density, so on the x-axis, and magnetic flux density on the y-axis. So in that first point from the ground to the knee point, you've got the easy magnetization period. So that's the kind of things you make a soft electromagnet out of. So something that you can wrap the coil around. When you apply the field to it, it will be turned into an electromagnet, and then when you turn the field off, the current off, the field disappears and it loses magnetization. So that's something that's easy magnetized with a low amount of energy. If you push that into magnetic saturation, so you kept increasing the field strength, you go into the hard magnetization area, which requires more energy, and that's what allows a material to retain its magnetization. So remember this diagram that we had in topic number 14's video. So if you initially got an unmagnetized piece of material, then all the magnetic crystals are pointing in different directions. So in this case, the arrow direct points to north. N means that north is pointing out of the page or the screen at you, and S means that the south is pointing out the page or the screen at you. So when something magnetized, everything's all higgledy-piggledy, so there's no overall magnetic field. If you apply a field to it, everything's going in more or less the same direction, whether it be up, whether it be down, or whether it be straight across. So that's when you applied, it's partially magnetized, so that's like a soft magnetization. When you drive it into magnetic saturation, everything is aligned, so everything just goes in one direction. So that's what's called magnetic saturation. Okay, so that produces a hysteresis curve, which is after the initial magnetization curve from here. So it goes all the way up and driven into magnetic saturation. Once it's at that saturation point, if you removed the applied magnetic field and it went back down to 0H, you would still have a magnetic flux density, which means it's retained its magnetization. If you then drove it into negative field, it would then go down here, like so, and go into negative saturation. And then if you applied a positive magnetic field to it again, it would then go around the curve and into a positive saturation point. And remember I said earlier in the video that moving around this hysteresis curve causes the core to heat up, and hence we have a hysteresis loss, which remember we resolve by using different alloys like the nickel steel alloy that we mentioned earlier. However, this also gives us one other useful piece of information, which is the area that the hysteresis loop occupies determines how much energy the material will take to magnetize. So if it's a relatively soft magnetic material, you'll get this narrow shaded area here, which is very soft, so it doesn't take much energy to magnetize. Where if it's a hard magnetic material, you'll see here, it's got a much larger area, which is this lightly shaded blue area here. If you want more information on magnetics, try and find the book Electromagnetics with Applications by Krauss. It is a really good book. As I said in the video, it's good for radio frequency applications, antenna applications, comms, that kind of thing. So it might also be useful to the 102 CEM students who are doing antenna theory, or for radar systems or things like that. So it might be useful to them as well. And it's going to be more interesting for the electrical students as well because of the magnetic stuff. Not so much for the electronic or the computer hardware software students. But yeah. And that brings me to the end of this video. I'm going to have to do some editing on this because there were numerous disturbances such as the dog barking and doorbells going off and phones ringing and things like that. So yeah. So I hope you found this video interesting, that it's resolved some of your problems, or hopefully all of your problems, and gives you some good preparation for the exam. I will be doing a face-to-face revision session on the 15th of January. And we'll post the exact time. I think it's at 2 o'clock in the afternoon, but I'll post the exact room and time just to confirm on the forums. So that will be on the 15th of January, 2 days before the actual examination. So have a look through this video. If there's any other queries, bring those along on the day, and we'll do that face-to-face session. Other than that, I will say have a very good holiday. Have a very Merry Christmas. Don't try to work too hard. Make sure you enjoy yourself as well so you can recharge your batteries. Do some revision. I know you've only got my exam, but make sure that you put the effort in to revising for that exam, because I want to make sure that you all pass. And I can't do that unless you put the revision in the first place. And yeah, that's it. So I will see you all in 2018. So take care, everyone. Have a brilliant holiday, and I will see you soon. Take care. And if you need anything, just give me a shout. So bye-bye.